Achoo! Alright, it's been a long time since I did physics, but 2 days until the physics exams. I just want to review something that I feel like I need help with, and might as well make a video, right? So this is E.3, where's my data booklet? Which is Radiactive Decay. So first what you have to know is the fundamentals of decay, or what types of decay happens. Within that, you know what nuclide is and mass number and all that stuff. But nuclide is a type of atom, so let's say Na, sodium, uranium, cesium. These are like common ones that might come up, especially uranium. And radium, which is Ra, and radon, which is R, I think. But that's not the point. And next is this is the notation, so which is the mass number, which is A, and then Z is the number of protons or electrons. If you do chemistry, you should know this. And X is basically like the name of it. X. So let's say it's 228 uranium and 92, I think. So this here is number of neutrons, plus number of protons, which is your mass number, and here is your number of protons or electrons, and here is your uranium, which is your element or atom. Okay. Isotopes, same. So it's the same number of protons and electrons, but different number of neutrons because A is different. You get A by doing, A minus C is number of neutrons. So different A means that there's different number of neutrons. Here is in classic one, carbon 12 and carbon 14. You see Z is the same, but A is different, okay? Next is the 3 types of decay you have to know. First is an alpha decay. An alpha particle is basically just a helium atom, or you can write like this. They're the same thing, but you have to remember that an alpha particle is a helium atom, okay? Here's an example. We want to find what TH is, and this kind of goes for beta and gamma decays, but they're going to ask, it's probably going to worth 1 mark, 2 marks, depending on what type of decay, but they're going to ask you to write the decay equation, which is this. And what you know, conservation of mass is that mass cannot be destroyed or created. Well, it could be. You just can't make mass out of nowhere, right? I can't breathe and all of a sudden 50 kilograms of, I don't know, glass just comes out. That's not how it works, right? Like, the amount I breathe out is the amount I breathe out, okay? So it goes for this. So we know that there's 200, the mass number for uranium is 238, and the proton number is 92. Both sides have to equal to each other. And so 238 makes something plus 4, okay? So 238, let's say this is A and Z. And I'm just kind of going into it because really, it's not that hard to explain. 238 equals to A plus 4. Well, then what would be 4? What would be A? A would be 234. So TH here would have 234. And down here, it's that you do exactly the same thing. 92 equals to Z plus 2, which then this equals Z equals 90. That's it. It's really that simple. Next is beta decay. I wrote 2 types of beta just for sakes of it. This, let me get the pointer. This is how you're supposed to write it. This is the actual thing. Like, if you write fancy and stuff, right? But I don't like to write fancy. You can see by my handwriting. So I just do this. And like I would just go, actually the right pen's better. So like you do this normally, right? I just do like that. It looks like a beta. It looks like a B. There are 2 types of beta decays. One is a beta minus decay, or you can call it an electron beta decay. But a beta minus decay is shown by this. A beta particle and 0 minus 1. It's an electron, okay? And keep in mind, you have to add an antineutrino every time you see a beta minus decay. Remember that. And an antineutrino is basically this. It's like a curvy V, and kind of go in and out like that with a little line on top. That's an antineutrino. And it's still the same thing here. There's no masses here, so it's 0, 0, which means you don't have to write anything. Okay. So beta minus here, I'll give you you pause the video if you want to do it, but it's the exact same thing as what we did with the alpha particle. All right. So both sides have to match up in terms of the numbers. So 130 on the top, there's 0, and the antineutrino is 0, so this would be 137. Down here, beta minus, so it's a -1. So 55 equals to x plus -1, right? So here, it would be 56, just like that. Next is a beta plus decay. It's a beta plus is same thing as beta decay, beta minus, but instead it's +1 here. It's called a positron. Electrons are in minus, but then we're rolling with it, right? It's a positron. It's a positive electron. And here, instead of adding an antineutrino, you add a neutrino. So without the little dash up here, right? Without that. It's like that, right? And this is an example. You can have some time to try it out. Okay. Same thing here. I'll just, for the sake of it, this would be 22, and this would be 10. Because 10 plus 1 is 11, 22 plus 0, and 0 is 22. But keep in mind, you have to remember this. Sometimes, if they ask you with a beta minus decay, it's probably, like, write an equation with a beta minus or beta plus decay, then it could be worth 2 marks, because you would have to write this part and this part, okay? So make sure you get that. And last is the gamma decay. It's just a photon. Nothing happens. Like, I'm just writing random stuff. 2211 forms 2211 Na plus photon. Okay, and that's the gamma decay. This will not happen, but then it's just an example. And remember 0, 0. And this is penetration and ionization, the ability. This one you should memorize, but if you can't, you can somewhat figure things out if you know. So an alpha particle is high in ionization ability because, well, it's a helium atom, right? But its penetration is poor. This is the part you can really figure out. It's like, we know that an alpha particle is a helium particle, so there's 2 protons and 2 neutrons. So this is big. Like, relatively, it's bigger compared to a beta minus or a gamma decay, right? So this will have the worst penetration ability, because let's say I'm hitting a wall right here, right? I hit it, it'll bounce away. Because it's that big, it won't go through shit. Okay? And next is a beta decay, beta minus, beta plus. It's moderate in ionization ability, it's moderate in penetration ability. And it can only go through a few cm of... alpha particles can only go through a few cm of paper. Your beta decay can go through only a few cm of animal tissue, which is, like the tissue in your body, or a few millimeters of aluminum. It's Al. And the last is a gamma particle. Well, gamma particles, they don't ionize. They don't have shit to ionize, right? It's 0 is 0. There's nothing. It's a photon, right? So it can't ionize. But the penetration ability is high. Because it's a 0, 0, right? This is a neutrino. Because it's like this, right? Then it's so small, it'll actually just fucking go through, right? Just say, fuck it, we ball. So that's why it can go through a couple centimeters of lead and a few meters of concrete. And next is exponential decay. And this kind of, we go through it later in the HL topic, but the nuclei doesn't come apart because of a strong nuclear force. Some properties of the strong nuclear force is, and HL listen, because I'm not going to go through this again in a couple minutes. But the properties is that it's short range, it's attractive, and it keeps neutrons together. Okay, it's an attractive force keeping neutrons together. And definition of decay, the properties of a decay is that it's random, so you can't predict which one will decay. So like let's say in a ball of uranium, right? There's so much little atoms in here. I'm lazy to draw. But you don't, this could decay, this could decay, this could decay, anything could decay. We don't know which one. And it's random. And it's spontaneous, meaning that it happens on its own, okay? So you don't have to heat it up to decay or something like that. Next thing you have to know is what activity is. Activity is the numbers of decay per second. Remember this definition because I think there's a worked example in the Cambridge textbook which asks about this, and you need this to start. It's the number of decays per second. It's in BQ, which is becquerels, yeah, which is the SI units, or in more simple units, it's decays per second, number of decays per second, right? Here are some key terms. Don't be scared about the writing. First you have to know what parent and daughter is. Parent is the initial nuclide, and a daughter is what it turns into. So let's go back. I'm lazy to write here. Let's go back to here, right? Uranium here, this would be the parent, and the thorium or thallium, I don't remember the name, is the daughter particle. Where were we? Here. Yeah, here. And background radiation. Background radiation is just the radiation around you. You know, like bananas, potassium has radiation. That also counts into background radiation. There could be some radiation in concrete, which will also count as background radiation. So you'll detect it. You know, like those little like clicking things you see on YouTube when people like go into terminal, they have a little clicking thing. I forgot what they're called, but then that just clicks, right? That accounts in every single radiation, every part. And this can be accounted, what did I write this? So it's not that important, but then really just for the sake of it, if you know, it's good to know. I haven't seen questions asking about it, but you measure the background radiation first. You do an experiment and measure all the radiation, and you subtract the background radiation, okay? Next thing you have to know is half-life. Half-life is is a time taken for the initial number of nucleons or particles or mass or activity to half, right? So here is a short example. So a particle has a half-life of 22 minutes, activity is 4,000 becquerels, and it decays for 88 minutes. What would be how many half-lives has it gone through? Okay. So what you notice here is that 88 is just 4 times 22. And we know that 22 is also half-life. So you can put this as 4 times the half-life. And so you know it's been through 5 half-lives. And we know the definition of a half-life is time taken for the activity to have, okay? So you just divide it one time. Ooh, that would have been bad. I don't want to erase. So initial is like that. So after 1 half-life, you divide by 2, which is 2K. After 2 half-lives, you divide by 2 again, which is 1,000. After 3 half-lives, you divide by 2 again, which is 500. And after finding 4 half-lives, it's 250 becquerels. So that's really it. Half-life. Just need to know time taken for things to go half, okay? Here is a decay graph. Let me move this over, actually. Oh, what the hell? What the hell? Ah, shoot. It's 2 on this. Alright, you know what? We ball. Fuck it, we ball, you know? So, your y-axis is number of particles or mass or activity, and your x-axis is time. So you have a graph something like this. It's kind of curved sound. It's a bit wobbly, but... So we know that here, this is from n naught, right? So after 1 half-life, let me get my little pointer. So you kind of find the half of it. So it's about here. So you kind of draw it over down here. And you go down here. So this is 1 half-life. When this number halves, it goes into 1 half-life. And you go from here and you half again. So it's actually bad representation. It's not, this is kind of half, but you get the point. Here, this is about 2 half-lives. And this is the parent nuclide because this is kind of going down, and when it's going up, it's the daughter nuclide, okay? What else? I had something in mind just now. Shit, I forgot. Bear with me, guys. Bear with me. It's fine. Background radiation. Do I talk about background radiation later? No. Okay, so here's when we have to talk about it. So let's draw a new graph. Okay, and this would be time. And this would be number of particles. Okay, and sometimes you would have a graph like this, like that. And you see here, when there's no change in the parent nucleons, there's still this amount of radiation, or amount of particles being, or like radiation, like decay, right? It should be zero, because once it's done, it's done. There should be no more radiation, right? If there's zero to fuse or fizz, then there should be no radiation being released. This is where background radiation comes from. The height from that horizontal asymptote is your background and remember how at the start here we talked about you can subtract the background radiation if you know the background radiation, and we clearly know it here, right? So let's say this is 3K, and it's asking for you to find the half-life, where the half-life is, let's say that. And here is, let's say, 1000. Okay? So what you would do first, to find the amount, half the nucleons that has or decayed, you don't just write 1500 is about here. That's bullshit, right? So what you do is that you want to subtract these two numbers first. So 3000 minus 1000 is 2000. So really your N naught, or your initial number of particles, is actually 2000. And and then you divide this by 2, which is 1000. And you subtract the 3000 minus the 1000, which you'll get into 2000, which is about here, right? And then you would go down straight here, and this would be your first half-life. Okay? And half-life is denoted by this T with a subscript of 1/2. Next is binding energy. The way I like to define it, or the way I learned it, is that binding energy is the energy required to fully separate nucleons, which is nucleons are protons and neutrons. They come in units of electron volts or joules, and you get them with Einstein's famous equation E equals mc squared. So you have to know is mass defect. In proper terms, mass defect is the difference between the actual atomic mass and predicted mass calculated by adding the mass of adding nucleons. But in simple terms, mass defect is the left-hand side minus the right-hand side of a decay equation, right? So here is an example. Radium, this decays into an alpha particle plus radon, which then, you add the mass of the radium and the mass of the helium and radon, and you subtract it. With this mass, which you can use E equals mc squared, because m is basically your mass defect, right? And you can get an energy, because c is just the speed of light, right? This is speed, and this is energy released. And you need to know that, did I talk about it? No, I do talk about it. After fusion and fission. I'll go through it later, but it's energy released. And just a note and it could be an exam tip too, M can have different units in this case. It could be in kilograms, which we're all used to, U, which is an atomic mass unit, or MeV, which is mega electron volts. Usually we like to use U, because if you look at your data book, let me see what section. Your fundamental constants, right? They give you U, and all the masses of electrons, protons, neutrons are also given in U, which I like to use. And you can convert U to mega electron volts, because questions will explicitly ask you to answer in mega electron volts, right? And you just multiply by 931.5 and you get 1 mega electron volt. So it's good. It's for lazy. It's more efficient, right? And here's just what I was wanting to talk about. After fusion or fission, a new atom is made, right? It goes from like radium to radon, and then some of that original mass is turned into energy. Hence, this is why there's mass defect. There's a difference in the energy, right? And it can be shown in the form of heat or light. That's why you see the sun, it's so hot and so bright, right? Because there's fusion constantly happening in there, and that mass is slowly turning into energy. And that's it. Next is binding energy per nucleon. The name really already defines the term because we know what binding energy is, right? So the way to get it is just divide binding energy in the number of nucleons. Here's a curve to show it. The peak of this curve is iron, which is Fe. And what you need to know, from going up, it's fusing. And going left, it's fizzing. Okay? Because, well, yeah, okay. That's what I wrote. That's all I wrote. That's all you need to know. It's a connection to E.5, which is stars. So you know stars have fusion in the cores, right? And this is really why they can't naturally... Well, this is why it's usually helium, hydrogen, and all that shit, right? Because past iron, it will start fizzing. Everything else here, before iron, everything before iron likes to just fuses, okay? So it doesn't fuse. In our Earth, because our mass isn't that big, it can't naturally fuse iron. However, some high mass stars do. I don't have anything on top of my head, but you just need to know. It's gonna be gone through in more detail in E.5, but this is all you have to know. And another thing to keep in mind, here it's actually not a smooth curve, but it's like there's like peaks inside, but this is sufficient. But you need to make sure there's a top and it kind of curves down. And that is SL part of E.3 in 20 minutes. Holy shit, I'm doing fast. Next is the nuclear stability and strong nuclear force. As I mentioned, HL, I hope you guys were listening. A strong nuclear force pulls the protons together. It's the glue that holds the nucleus together. Because, I'll just go a bit in detail. Because we know that nucleus is neutrons and protons, right? And protons repel each other. They don't like each other. They're like same charge repels each other. It's kind of common sense. But then the strong nuclear force is what pulls it in. It's what makes the atom an atom, what makes the nucleus together. And here's the Rutherford Geiger-Martin experiment. Remember this? They could ask you to talk about the findings and prove that the strong nuclear force exists. This is the chapter you want to know. So what they did in this experiment is that they shot a beam. They shot a beam of alpha particles to a gold foil. And what you would expect is that it would just kind of either stop or go straight through. But then what really happened was that the alpha particles start scattering. This is also known as Rutherford scattering. And some of them, they turned like that, they went straight in front, and some of them came directly back. And so it tells you, first, it tells you that the nucleus is positive. And this also proves that the strong nucleus force exists is because the experiment gets fucked when the alpha particle is shot at a high energy. And fucked, I mean it's broken. So what really happens when there's so high energy? We know that Ek equals 1 over 2 mv squared, right? M is constant and this is half. So if this what we can conclude from this actually is that Ek is proportional to V squared. Okay? And so higher energy means higher velocities of the alpha particles. And because the alpha particles are so fucking fast, right? It goes so fucking close to those little nucleuses in the gold. It goes so close in there. That actually just joins them. That's why it stops scattering, okay? So it pulls the alpha particles in. Another piece of evidence is that of a strong nuclear force existing is that if we go back to the binding energy per nucleon, that graph, is that after Fe and a bit after that, it's relatively flat. It's not that, I didn't draw it that good, but it's relatively flat compared to like the start part, right? And it gets slowly, essentially, it will eventually get constant at higher values of A, at larger values of A, yeah. And, this is actually because, it just goes in here. It kind of goes into the stability of the nucleus. So let's go through this first. Is that the stability, this is the graph showing the stability. The axes are actually just number of neutrons. Where's my note pen? Number of neutrons and number of protons, right? So here it's kind of one. This is going with the line where n equals t. One nucleon, it makes one proton, and it makes the whole thing stable. But after around when A equals to 15 or to 20, somewhere around that, it goes up here. This is more proof that that strong nuclear force exists. Because you're needing more neutrons to kind of, or actually no, that isn't. You need more neutrons to sort of stabilize the protons before everything starts bouncing out, right? Goes everywhere. Yeah, and oh yeah. Yeah, okay. Type shit, my bad, bro. Is that, yeah. How should I make it human? Make it like simple terms. It's that, yeah, oh, here. Let's just say this first. This orange line here, because it's more steeper, you need more neutrons to stabilize the protons, is that more protons means that there is more electrostatic repulsion between the two protons. So we'll go that and that, right? So you need more neutrons to keep it stable. Oh, okay, yeah, I remember what I was going to talk about. Yeah, so this is basically your strong nuclear force, right? It's keeping everything together, it's keeping it stable. The next part for HL is the decay constant. This is the last part you have to know. I would say most common, most useful, I would say. Because topic E usually asks you in the paper 2 question. But your decay constant is the probability of a decay in a given time. A tip I would like to give you guys is watch out for units. It could be in seconds, it could be years. Same thing for half-life. Oh shit, I forgot to tell SLs. Now they're gone. Fuck. It's fine. Just watch out for the time. Because sometimes they'll give you in seconds, years, minutes, hours, etc. and all that shit. And you want to convert it to the correct unit, to the same unit, and it'll be apparent. But, yeah. So, these are the 3 equations. N is the number of particles. Let's write this down together. N is the number of particles. And naught, which is like a with little 0, is initial. I fucking spelled it wrong. Initial number of particles. Half-life. Oh, A, which is activity. When did I talk about activity? Oh shit. So activity is given becquerels. Which is, I swear to God, I wrote activity somewhere. Jeez. Oh yeah, here, yeah, we talked about it. Yeah, activity in becquerels. It's decays per second. Activity, which is, okay, have fun. And lambda, which I know it will be confusing because wavelength is also lambda. But when you're looking, this is where I have to differentiate. Use your brain, okay? Waves and, atoms are 2 different things, okay? This is where you need to come and differentiate what the question's asking for. But then lambda is your decay constant. And T is your time. Okay? So all this kind of relates to each other. And yeah. I mean, you start with this equation, and we know that A equals lambda n. All these is given in your data booklet. And you know, since A equals lambda n, you can kind of plug in this. Ooh, I don't want it. You can plug in this here. So A equals lambda m naught e to the power of negative lambda t. And E is Euler's constant, like the little shit, you know? And half-life is ln2, which is natural log, divided by your decay constant. This is something you have to know, how to derive your half-life equation from going from here to here. Kind of wrote it down, okay? So n equals to n naught e to the power of negative lambda, okay? And we want half-life. We want the time it takes to half. And so t, we know already equals to half-life. And n naught, because half-life is given as the definition of time taken for half the particles to decay, well then, half times n naught. What we can do here is that the n naughts cancel out, and you're left with this. You ln everything, which if you ln here, you get ln 1/2 equals to minus lambda times the half-life. ln1 over 2 essentially is just ln1 minus ln2. ln1 is 0, and the minuses, they cancel out, which you're left with this. Voila. That concludes for... Scroll up. That concludes for E.3.